Okay, can you hear me? Yes, no?
Yes.
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 All
Yeah.
right. How
Yes.
are you?
Yeah.
Good. That's good. Oh, I am super tired, but that's okay. Um, I have everything okay with the audio. Sorry if you hear like a noise of machines like in the back. Probably you will hear it, probably you won't. It's like MIT is always under construction, so it's like New York City. So you're always interrupted by uh, external noise. So I send you over email the files from day 1 and 2, and also I send you, it's a Dropbox links. I'm a Dropbox link where I have the files. Uh, Everything is working. So you can play, check, see the difference with what you're doing. And also I uploaded the basic script and config file that is exactly the one that we used yesterday for training and doing what we're doing today. Because today we're going to build upon the example from yesterday, and we're going to go even like one step higher in complexity. And I will show you what we're going to do, since it was requested to show what we are going to do. Even though I like to keep the suspense a little bit, uh, I always want to do that. Just give you like breadcrumbs so you follow me, and then I show you like the big act. So session 2, we programmed this simple agent that, let me open the file, that was moving in one direction. I will share my screen in a minute. Uh, Screen 2. And before, can you see my screen, Unity? Yes? Okay. Um, Also, the video is still being like encoded by YouTube. So sorry if it's not ready yet, but it was uploaded. I sent you in the description of in the email about the video. If not, if you subscribe to the YouTube channel, you will see a playlist that is called Smart Collaborative Agents, and you will see as a video too. This is still processing, so hopefully it will be done soon. But I also I shared with you the Dropbox folder. Uh, okay, so this was the example that we used yesterday. I will add a trail renderer so we can see basically what this guy was doing. And also, as an option, um, I will explain one thing. Let me set this to 10 maybe. The ML agent, it has the basic training file, yes. So if we run this, you see that the trajectories that the agent is following are, as I was saying yesterday, like very discrete, right? So, but you can see now that after training this, we have like an autonomous behavior that is actually quite good. I trained this probably for like 10 minutes, and the agent is capable of following a logic, right? Following a target. So I think it's like pretty nice, because in one day we just program something that is like super complex. It has like, let's say, agency on its own to follow the target, and you can do like a lot of tweaking to to the way that this agent basically follows the cube. So right now, you see when it touches the cube, it resets the episode. It's not necessary that you do that. You can set like, from now that you have this behavior trained, you can set like any type of new behavior, interaction, and so on and so forth. So you can also have like multiple targets, for example. You can set target one, for example, a simple target, and then you can say, oh, what if I, for example, said when I reach the target will change to a location. So you can set, for example, like, how do you call it? Like a specific points, right? Or the agent will follow a sequence of points to do something. When you're in this position, do something or pick something. Then when you're at this position, drop something, right? So we will see how this will evolve. So this is very important, for example, here, because the discrete movement says that we are moving, as I showed you yesterday, in 0.15 units. Basically, that's the step move that we program our agent to do. It cannot reach the agent, so it's like in an infinite loop. And this is on purpose, because remember that we just programmed like 4 actions: up, down, right, left. I told you that you can put more, if you remember, actions, like a 5th actions to go diagonal, and that will solve this problem. Also, you can decrease this number and give it like a lower number. Of course, it would make it slower in the times of response, but you can see that now it can do like, the agent can do like micro steps to follow the agent. So these are things. This is important to have, as I was explaining yesterday. These are really important things to have as public variables, because especially in today's exercise, that I'm really excited. I don't know if it's going to completely work now, because it will be harder to train. I did it a couple of years ago for another project that I was doing in my school in Chile, where sadly I lost most of the files, but I recovered one that we are going to use today. So yeah, you can see this. So you will have this. I'm sharing this project, where this project has the config file. I'm using the basic. I mean, you can delete the trainer config and trainer config too. I mean, this is the one that it works off the shelf. And before I go to reveal what we're doing today, again, for the ones who probably forgot about it, remember, these are the 4 actions that we program. We can program movements in diagonal and so on and so forth. And that will be like amazing. So enough of this agent. We are going to create now a more complex type of agent. And tomorrow we will create another type of agent. So my goal for this workshop is that we finish at least 3 types of agents. One that is like really basic, that basically moves on the plane, just like we did yesterday. We will do another that has surprise behavior, but as probably you know, because it was part of the description, I want you to create a final agent. And this is the homework that I have to assign you for tomorrow. If you cannot do it, I can share a file. Can you see my screen, the Rhino file? Yeah. Yep. So I want you to prepare your own robot, your own robotic arm. So this is just a simple Rhino file. Sorry about that. This is just a simple Rhino file that has 6 axes. It's a 6-axis robot that we will use to train, use machine learning agents, ML agents, to train this robot to reach a point in a similar way this basic agent did, without any inverse kinematics involved. So that is like actually quite cool. So we will not get into that. We will just like tell our agent rotate like this, like that, and so on and so forth. So you can basically reach this. This is a super difficult task. This is why I was saying the first day that don't expect, don't be surprised if the results are not that precise, because we're not looking for precision in this workshop. We're just experimenting and having fun and having like a foundational knowledge, so you can basically continue working with this. Um, I I've been working with this for a while, and now that Unity released actually one example with robotics, it made my life so much easier, because it's actually pretty nice to train with more accuracy, because they provide now a very nice articulation system that we will use. And it's in one of the examples that they provide, and we will build upon that example. So the idea is to combine 3 agents probably to do something for this workshop if you want, right? So the assignment is to have hopefully like a Rhino file. It could be like a Fusion 360. We want to have a file that has like separate meshes. It could be like an FBX that contains all of this, or you can export individually all these parts. That will be okay. But hopefully it's built in a way that, for example, the pivot, it's accurate. So for example, here you know that this link pivots in this point. This one, the pivot rotates around this axis. This one rotates around this axis, and this one rotates around this axis. And we will use like one default end effector that I will provide. So if you have this as a mesh, tomorrow we will prepare this and we will program the behavior and we will do it. So this is super exciting because you will see that it works so well. I mean, it's so amazing to see this complex thing doing stuff. And I will show you all the other examples on how to do this in a more autonomous way. For example, there are ways to do it with other algorithms. Like someone asked me like what we did. 1 second. Like for example, someone was asking me like if the first day about like A star, for example, and if this could be applied for robotics. And I was saying that there are other more advanced algorithms that are used for this. So for example, RRT or RRT star that are often used, for example, in intelligent robotic manipulation to calculate the path or how the arm will move and grab something. So it's like a similar alternative way to do it, and it's exciting that it opens up a couple of possibilities to do stuff. Yes, Pedro. Now, sorry. Pedro?
Quick question. Do you want us to develop like specifically a robot, something that rotates, has access, or is more like open-ended? Could be like any creature, agent, whatever that.
I will work with with this robot arm, but the good thing is that you have the freedom to do pretty much whatever you want. You can do the creature with, I don't know, 4 arms or whatever, right? So basically the minimum knowledge that I will provide on how to configure this robot and set it up and whatever, it will be general. So if you want to add more links, if you want to add like other stuff, so yeah, it's completely free. And actually it doesn't have to be I mean, this specific, let me this this methodology, it doesn't work specifically for robotic arms. So let me see. There is one example that I really like from ML agents that uses a similar concept about like these rotational links. Probably I can show it to you. I'm trying to find it. Sorry, that is taking a while. In the original Unity, in the paper, basically about ML agents, there is a paper that is really famous. This example, this particular example, that is a worm with eyes, it's like really, I don't know, like cheesy. It's just a configuration, just like the robotic arm, that basically has the possibility of just rotate the joints, the links. Can you see the paper? Yeah. So can rotate the links. This is one of the default examples that they provide. So basically, it just starts moving like a snake towards the target. And it's really interesting because, yeah, what we will learn tomorrow is basically this example, but applied to robotics, but it's like very, very general. So enough with the suspense. I will provide the, okay, you're okay with this. I will share also this file in case you don't want to model any, nothing, but it will be nice if you can. This is pretty like a universal robotic arm, really simple. So if you don't want to do anything, you can use this one, or model your own if you want to test more custom things. Oops, something happened. Okay. So let me start Unity again. Hopefully you will start Unity as well.
Theo, I have a quick question.
Okay.
My question is about having multiple, agents in the room, not multiple agents, but having several examples of these agents and targets in the scene, like the arrays that you showed the other day. So when I do so, when I copy paste this agent and the whole scenario one, like for 20 times, first of all, it's really slow. And I realize that for each sample that I have on the scene, it trains one separate neural network. Is that the way it should work?
So can you, again, I lost you for a bit.
Okay, so I tried to have multiple of these, agents and targets, and copy pasted them, like 20 of them, on one scene. And I tried to train the model on that, array of agents. I realized that the machine learning backend trains, for example, 20 different neural networks simultaneously. So is this the way it should work, or they all should use the same neural network?
It's the way that it should work, but they all basically contribute to the final weights. That's the way, at least that's the way the engineers from Unity explain it at the GitHub, because this has been like a recurrent.
Yeah, but when I'm checking in the results folder, I realize that it has something like 20 different neural networks created and trained. And for each agent that I have, for each ML agent that I have, it's trained one neural network. My assumption was that they all should contribute to one neural network. And then I assign that trained neural network to all the agents, and they are all going to work. But right now, maybe this is a configuration that I have, like it might have been set incorrectly, but I think it's too many networks for one model. If you have some time later today, it would be great if you just show us how that one is, and those distributed ones can be actually configured.
Yeah, I can check, and I can go about.
Great, thank you very much, appreciate it.
So today, who likes drones? No one? Drones are boring? Good. So today we will work with this little guy. We will try to train it. This is a really old project, as I was saying, that it's based on the code from one YouTuber. Don't remember the name because it was like probably like 4 years ago. So we will work with this guy that can fly, can go up, can go down, can rotate, can do like a lot of things. So we are not only work, as you're seeing, with a drone that can, or an agent that can reach something on a plane, but can actually learn to fly and reach a specific target, right? So if we check, we'll go first to check the script. I will share the script also in the chat so you can have it in case you didn't see it in the email that I sent. Let me do it.
How long ago did you send that email?
Probably like 30 minutes before the class. It's a Dropbox email. That's the only way I share files. So I'm sorry if you don't have a Dropbox account. I mean, I put the link in the chat for everyone, so it's the same thing. But in case you want to, I don't know, collaborate with something, you can do it. Show in Explorer. I will share this guy here. Can I just drag it? Oh, I'm sorry, in meeting file. No, I'm good to go. Okay, this is simple drone. I just shared it with you. So let me open it. Because also it will, can you see Visual Studio Code?
Yes.
Perfect. So this script is like more complex, this chunk of code, because this will set the base for how are we going to program our agent. And it has like a lot of things that involve also like simulating with real physics. So adding forces and rotations, and also like managing the way these forces don't go like crazy, and so on and so forth. So I will try to explain a little bit how it works. In this case, we don't have a target, so I can erase this. So here we have like the common parameters. We have parameters that are related to the movement. We have the possibility with this drone to, basically it's just like any like phantom drone, for example, to move forward, move backwards, and that creates basically like the tilting. You can basically tilt and move to the sides. You can rotate, and you can go up and down and combine all these movements, right? So that's the way it works. And we will modify this code in order to train it. So we will write some parts. But the way this works is the following. We have, again, like the variables for like movement forward, for rotation. I will explain this in a second. Also the limiting speed variables, because when you're working with physics specifically, for example in Unity, and when you're in ML agents, you don't want something that can go like really crazy, and basically the training gets like super complex. Again, this is experimental. I made this work with one of the probably like the last time I trained this was like 2 years ago, and it was working, but it was taking like more time to train. So I will leave the training up to you after the class. Here, as I was explaining yesterday also, we have, instead of the update function, we have the fixed update, because it's basically a fixed interval between frames that allows us to have more accurate physics. Every time that you have physics, you want to have that. And then you program the movements, in this case, are just like manual movements to control your drone. And we will modify all this movement up, movement down, movement forward and backward, and rotation, and clamping the values. So basically it doesn't go like, again, too crazy, and how it's swerving to the sides and so on and so forth, in order that our ML agent can basically train this this drone. Okay, so first things first, I will create my drone from the beginning so we can model the same thing, because it needs to follow a specific structure, as you can see here. So let's do that. I will create a new scene. The first thing that I want you to do is to create a plane object. Right, you go to the hierarchy tab on the left side of your screen, and we will configure this to the position will be 0, 0, 0, and the size, let's give it a good size. This can be also 0 or 1, it doesn't matter. So we have a large field for our drone to perform whatever it has to do. Right, super simple, just a plain object. The second thing that we want to do is create an empty game object that we will call our drone. And inside this empty game object, we will create the body of the drone. In this case, it's a cube, just a simple cube that you can assign with materials. I have a couple of materials created. Remember, if you want to create a custom material, you just right click inside a folder, in this case, the folder materials, create material. And here you can say like, I don't know, like magenta, for example. And you create magenta, and here in the inspector, you can change the characteristics of magenta. You can make it more metallic if you want, or whatever, like more smooth. It's up to you. We will we'll paint this object magenta. All right, so that's good. Now, what we can do, we can clone this cube, and we can give it the position. So basically our drone is oriented like this. This is X positive, Z positive, and Y positive. So we will create the propellers, basically the motors. We'll send this to 1, to 1, and to 1. This is the position 1, 1, 1 in the cube. We will set the scale to in Y to 0.2, maybe. It should be a little bit lower. Let's set it to 0.5. And with this, we will have the first, this will be the right front motor, front right motor, right? And I will give it a specific color. The front motors will be red in my case. You can do it whatever you want. I will copy this, and this will be the same height, but a different X. So it will be -1. You see, I have another one. This is the -1. And if I copy this one again, this will be the -1, -1, and -1, sorry, 1 and -1. So that's the way you do. We will say that these are the motors of our drone, and this is the way that this guy is gonna fly. So we can name this. This is front right. This is front left. This is back left, and this is back right. And everything, as you can see, we can say like this is the drone body or whatever. Drone body. This is the basic structure of the drone that we are going to use. For now, we're not going to include the camera inside the drone, so don't worry about it. We will not turn this into a prefab. This is something that I didn't talk about yesterday. You can create like some sort of like the typical like AutoCAD block that is like that are this types of components that you can replicate and modify, or like a Revit component, for example. You can modify and you modify all the instances of this. But we will do this later once we finish configuring this. Any questions so far? No? Okay, so let's start programming this. We will, just let me copy the code. Let me do one thing and we will start coding. Okay, I'm saving this and good to go. Also, in the meantime, I'm sorry if I'm not as fast in replying your emails. It's just that after this, I have to work because we're with a deadline for my lab, and it has been nightmare. I'm sleeping like nothing, so please understand if it's not that I suck as a workshop host. Hopefully, it's just that it takes a lot of work to. Probably I'm one of the only ones that are teaching a workshop alone also in this conference, because I was told to do it like at the last minute and everybody's gone here. So, and also that proves that I'm probably the only one at my group at MIT doing this stuff. The other ones are doing shape grammars and similar things. Okay, so, okay, here's giving me the typical like miscellaneous error. So let me repair that. I don't know why this is happening like so often. So edit preferences. I just click a couple of times and it should fix it. So scripts, simple drone. There you go. So first we will do our imports using a system. If you want to write it with me, that's fine. You have the file, so it's not mandatory, but I will try to explain everything in a better way. Right now, I will try to do it fast, so then we can modify it, and then we're good to go. System.collections. I will just, this is something really, oops, I pressed the wrong button. Okay, so basically we have like the typical imports. We don't need anything else. We will say that this is a public class. Oops. Public class. We called it simple drone, and this inherits from mono behavior. So now we're good to go. First things first, what we need to do before start coding we need to go to Unity and do one more modification to our drone. Here we want to add a rigid body. We want to add a rigid body that basically gives us the possibility of doing the interaction with physics. So we can set this to 10. We want to use the gravity, and that's the only thing that we need to configure here. So this should be okay to just start adding forces and rotations and so on and so forth. So you should have the rigid body here in the main, let's say, like root of your group of objects, in the parent object, actually, that's the way it's called. So we can access to that. So we will first add something that will be useful for later. This will be like the control variable that we will call public bool is manual. We set it to false. This will control, we will use this not now, but when we are training our model, because this will give us also, if we have time, to show you how to do imitation learning, basically train an object based on samples. So that will be like, basically I will give a demonstration to the neural network, and the neural network will try to replicate that. So basically I will provide the experiences. So, and also to do the demo that this is working, of course. We don't have game object references, so we need to access the rigid body of the object. This is rigid body drone rigid body. So we will say rigid body, and we will call it just like yesterday, RD. And we need a first method, private void awake. Awake basically is the first thing that even like before starts, if I remember correctly, executes. So on awake, before anything starts to happen, we will get the component. We will say that RD is equal to get component rigid body. Remember that in this case, we are applying the controls inside the drone agent. So we are not, basically we don't have to do like the typical thing of game object, agent, as we did yesterday. So we will do everything in this file. This is another approach. So if we were doing like this type of thing, we will have to do like agent.getComponent. If we don't do that, because we are applying to the same object, we can access directly all the other components. So this is why game object. Okay, that's okay. Now, as I was saying, we need also a private void fix update method instead of the update. We're going to say that this is good for physics simulations. And we will add a couple of methods that we want to use. The first one will be movement up. And this is a method that we don't have that we will create here. So we will say void movement up. Movement up Okay. And we want to do, we want to program basically the capacity of just like flying first, like a vertical fly, like lifting from the ground. And to do that, we need a couple of things. We need to declare, we can do it here. Movement up and down variables. This could be a float. And this float, we'll set it to public so we can see it. Public float, we'll call it up force. Yeah. So here we will say, first things first, if is manual equals true, if we're setting this to manual mode, we will basically execute everything. If not, we will do the things that we need to do with our ML agent behavior, right? So this is very good. Again, we are doing this just in case today, if we have the time, we will try to set everything to, we will try another type of training that is imitation learning. So this is why we need this. We need to be able to control the drone. If not, we will start first with normal training, and we can do like the first part of the session tomorrow to doing this. So we will say that if input that get key and parentheses key code that this is with case key code dot we will use the key I. If we press that key, our up force will be equal to 450 F. It's a float. Basically, we will give like a huge amount or like a good amount of force to our object. We can change this later. We can tune it because we don't know how the training will go. So that is okay. I think that's okay. Yes, that's perfect. So actually, we can call this like movement up and down now, but we will do just movement up. So the script will be a little different to the one that I gave you, but you will see the difference. We will add another method here to go down, movement down, and I will copy this. Let's make it a little bit prettier. I will copy another method, and this will be called movement down. And the same thing, if it's manual, do this. If we press here the key K, our force will be, we can give, I don't know, like it was minus 200, so we'll leave it to minus 200. So this will make the object go down, not as fast as it went up, not with the same amount of power. Probably it will, because of gravity also, they will go probably at the same speed. And now we need to check if this works. So here we will add the forces. How do we do this? We can call the RD component, and we can say that add relative force. And relative force has like many ways of using it. We can provide, for example, a vector, a force mode, or just a vector 3 that indicates force. So in this case, we will say the force is vector 3 dot up, because it's moving up, times up force. See, so this is very like easy. If we press I, the up force will be 450, and because this is multiplied by the vector up, this should lift up. So let's try this. I will compile it. I will go back to Unity, and let's see if this works. It is. Oh, sorry. I need to press. I didn't apply the script yet. Sorry. That's so dumb. Simple drone. And we're gonna check now that this is manual. You need to apply it to your game object. So if I press it, it goes up. If I press the K, it goes down. So it should work the same way for you. You see? Boop, 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 boop. And sometimes it does weird stuff. So with this, we are okay. We know that this system is working, and because it's also working with physics, it's actually quite cool because it gives like a more realistic simulation. The similar thing will happen with the robot that we are programming. So if we go back to the script, we want to program now how the drone can move forward. So we create the method, and we call the method. We create the method here. You can comment it. I hope it is commented. No, it's not commented in the file that I gave you, but it doesn't matter. Move forward. It's pretty like clear, at least the names. To move forward, we will repeat a pretty similar thing. We will leave the structure of the if is manual true. We will control it with the keys. But now for forward, we will get the axis. So Unity had different types of inputs that you can configure in your preferences. Where are the project settings? I think it was. I always forget where are the inputs for this. It doesn't matter. I will show you tomorrow this better. So basically, you have like predetermined behaviors, and one like accessing, like for example, like the vertical, like simulating the joystick, the vertical axis or the horizontal. You can get values that are mapped between -1 and 1, for example.
Diego, I think it is in edit project setting, and inside project setting, it is in, yeah, that one, input manager under access.
Thank you.
Welcome.
Yeah, so you have here, for example, horizontal, and it gets like key or mouse button, or you can have also a joystick attached to this, and you can map the values. You have like sensibility, the gravity, and so on and so forth. We will use this tomorrow in terms of like creating our own. For now, we will leave it like that, and we will use some of this. I mean, it's good that we just know that it's there. There's nothing too special to know about this today. So we will say that instead of get key, get axis, and we call the axis by vertical, without that, not 0, not equal 0. We will perform the following thing. Oh, I already have the bracket, sorry. We can say that RD, our rigid body. I don't know why I call it RD. It should be RB. Oh, rigid body drone. Okay, this is why I told you before that I'm bad with names. We will add a relative force now. It's happening just in a force that is relative to the coordinate system. So we will do the vector 3 that forward times the input that we get from that axis. So input that get axis vertical times here we can create a new variable, and that variable will be, let's put it here. Oh, sorry, this movement forward. I will change the name. This is what is giving me a mistake. Movement forward. I will create a new variable here. This should be, let me see. We'll create 3 for this purpose. One will be a private float move movement forward speed equals 500F. The other one will be private float. Yeah, because in the end also we want this to tilt. So this will be tilt amount forward equals 0. And this will be a private float tilt velocity forward. Tilt velocity forward. That's okay. So if we do this, where were we? We will multiply this by movement forward speed. So we will add that. We are moving, the force is added relative to the coordinate system of the rigid body, and it will move basically with the vector forward. It will add so it will push it forward basically by the amount of the axis vertical and this multiplier that we have here. And here we can add, for example, the tilt amount forward, because then we want to control also the rotations. So I will do this immediately. We will do this as map F smooth damp. So basically this is a function that decreases the value over time. We can give the tilt amount forward. We will give it here probably like a 20 because it asks you for the current float, the float target, the maximum, and then the current velocity, and then the smooth time that basically you need to decrease. So here this will be actually 20 times input dot get axis, and this is the vertical axis. Vertical axis, I'm missing this guy here. This is a reference value. This will be tilt velocity forward, and this is 0.1 F. So it will decrease like slowly. It will smooth the value like constantly. So you know when the drone is like trying to go forward, then basically it goes back to the position, like the typical drone. If you move it forward, then it will try to go back to the horizontal position. Doing this will save a lot of, I mean, if you can find, for example, ML agent tutorials or videos and on YouTube. I think there was in YouTube or Vimeo of a guy that had something like really cool trying to train a drone, but he was not controlling. He got like there's a video, like an old video. A guy is trying to train a drone, and the drone is always like jiggling, like doing weird stuff, and it was because he never had this type of functions to actually regulate this. He was training how horizontal the drone should be. So that was an action of the ML agent, and it worked, but it was giving like a nasty type of movement. So I'm trying to follow another approach. I think we're good with this method, so we need to, are we okay? Move forward and the axis. Oh, actually, yeah, we can do the movement backward. We can copy everything. I know that it's ugly to copy stuff. We will put this method here. And this will be -20. It should bring the drone and this should be back. I'm not sure. I'm gonna leave it like this, or maybe I'm not gonna use this method yet. I'm not sure. I did it in the script that I gave you in one way. Probably I will follow what I gave you in the script. So actually, if I did that, this is movement forward. Sorry for this. I just don't want to deviate from the plan that much, and I'm already getting excited about doing new things. Movement. Oh, and I copied it twice. Sorry. We have movement forward. That's okay.
Diego, I'm testing it with a joystick, and when I'm pushing the vertical axis back, it's basically moving backward. So it does the job. Do we need to have one forward and one backward function, or one of them is enough?
I want to do it like that, so we have this as a discrete action that we can use later with our.
Oh, got it. Makes sense.
Yeah, but we can modify it later. I mean, for now, I think I will leave it like this. So I'm trying to go like fast so I can explain and you get a sense about what we're doing. So each time we're just like adding the relative force that will allow us to just like take off or go down or move forward or move back. So we can add the rotation as well. I'm gonna speed this up a little bit because it's already 3. Yeah, I want to finish this part before the break. This is a method that, again, if it's manual, it takes the J key in your keyboard and basically makes a different. It subtracts an amount of rotation to the current rotation. So basically, it can rotate around the y-axis. And if we use the L key, it will rotate in the positive like direction. So this will rotate left, this will rotate this will rotate left, this will rotate right, and we will set the current rotation here, and then we will add this also to the rigid body. So we need to declare these variables for this. These are the variables. The wanted rotation that we will calculate, the current rotation that we need to get, the some sort of like multiplier for our movement, and also the rotation velocity that we will calculate. Once we have this rotation function, you see that it's also modified by this damp smooth function. If you look at the documentation in Unity, it explains a little bit. It says that here, gradually changes a value towards a desired goal over time. So this is why we're using it. The value is smoothed by some spring damper-like function. So you can learn about all these weird methods if you go to the Unity documentation. So trust me, I mean, it should hopefully works. So now we need to take care of the rotation of our drone. And for that, we will do rd that rotation. And for this, we will use quaternions, that Euler. And we will do vector 3 dot, not dot, vector, new vector 3, sorry. Vector 3. And here we will add the tilt amount forward. Yes, for the first component. We had the current Y rotation. And here we will add the tilt amount. We need to add another one. For now, we will leave it to 0. We need to also calculate the drone like tilting to the sides. So for some reason, this is giving me an error here. Relative force.
You just have a space between your vector and 3.
Yes, is that it? But why is it giving me here vector 3?
Oh, is it lowercase?
No. Whatever, I have it here also in my notes, so I will copy that. So hopefully it won't give me a problem. Let me see. Did I write anything like special here? Nope. Everything looks okay. That looks okay.
Maybe it's accidentally importing the system's numeric thing again. That is confusing the.
Oh yeah, I don't know why it does this. It's doing it automatically, so. Oh, and up force here is like this. Okay.
Shouldn't be like RD dot rotation equals to that quaternion?
Yeah, equals. Yeah, you're right. Between all that amount of parentheses. Thank you. Just realized that. Okay. So basically, we're setting the new rotation according to this quaternion that we're giving here. So it can rotate on one axis and on the x-axis like this, the y-axis like this, and then it can also do this type of, I don't know if you can see my hand, yeah, like this type of movement. So we have the rotation. We can add also a way to the swerving. Call it here, you have it in the file. So the swerving method, again, if it's manual, we will get the horizontal axis. And we will, in this case, say that if it's bigger than 0.2, the amount of like the value that we're getting from that axis, we will add the relative force to the right and multiply it if it's either by values that are minus closer to -1 or to 1 to basically tilt to one side or the other. I need to create these factors that we have. So these parameters that are like some multiplier factors. I will do this here. I would say that the side movement amount is 300, the tilt, and we have these parameters that we need to, that we are calculating here, of course, the tilt amount sideways, and yeah, and if we don't get anything, basically this will stay the same. So we also need to add this method here, swerve. Here. So for the ones that are just beginning in Unity, basically we are calling these methods in like every update, but we are just checking the events inside those functions. So if nothing happens, they will remain stable with the values that we're giving. And if we basically push a key, it will create some movement in our object. So I will build this, and don't forget to save your project also. The last thing that I did for this example is that we need to set some sort of like clamping values. So the movement of the drone is not too crazy. So right now, if I try to run this, the drone, it's like a little bit crazy. Let me do one thing so I can show you. I will put the camera with the drone. So now, yeah, we're flying. And if I move forward, it is like a little bit too, it's not rotated for some reason. It's not moving. Oh, I need to add also the other methods. But basically the movements are like too abrupt. So we need to clamp those values to have a better movement of our drone. And let me check here. Yeah, we didn't add the rotation also. So the rotation and the swerve. Swerving like whatever. Oh, it was there. Let me see if this works right now. And we can finish this script. Yes, it rotates. It goes down, apparently. Yes. It leans forward, backwards. It works. So now we need to add a final method. That one will go here. And I will just copy it because it's a long one. So we can start working in the meat of our training agent. So again, if the values, so we're getting the absolute value from the vertical axis, and we're saying that if this is bigger than 0.2 and the absolute value of the horizontal axis is bigger than 0.2, the velocity of our rigid body will be clamped between, basically we will get this velocity and we will clamp it between these values here, right? So we will basically try to keep it within like some reasonable bounds so it doesn't go all crazy. And we need to add one variable here, and it's when the velocity, we smooth and damp it to 0. So basically here when it's minus 0.2, minus 0.2 for both axes, we will try to decrease everything to 0 so it doesn't go too crazy. Movement up, movement down. That looks okay. Let's see if it works. And if it works, we're ready to start now adding the ML agent part. So, yeah, yeah, yep. Forward. It's not leaning to the sides. So let me see why. Swerve. Horizontal, horizontal. Oh, I know why. Because we didn't add it. We didn't add the last value to our quaternion. So it's tilt amount sideways. And we are calculating in here. This is why it was not working. It always happens like that. So now it rotates, and yes, exactly. What a good drone. So now we have full control of this drone that is slowly falling down. So we're good to go. I mean, it's a complex, pure Unity type of script that it will help us to now assign the actions that we have. I will stop sharing for a little bit. This will help us assigning the actions that we have. So let's see, if this is my drone, right? We know that we have, and we need to this now. This will determine also our observations and actions. For observations, if we want to do the simple task of having a target, and we need our drone to get the target, basically the observations compared to what we did yesterday will be pretty similar. We don't want like any other observation, unless we want, for example, to always observe that the drone is at a certain height or things like that. We can start adding more layers of complexity to that. But for now, we're just going to focus on doing the same thing we did yesterday, of just checking the distance from one to the other, and that will set our actions. But for our actions right now, what we are going to have is movement up, movement down, rotation to one side, rotation to the other side. We have 4 actions, right? We have like the tilting to the side, tilting to the other side. We have 6, and up, down, and forward and back. So basically, we will have now 8 actions that we need to map, and that gets like very complicated because now these actions depend on a lot of other factors, such as and we will see. Like in terms of the training, we will just use like the same basic training file. We will not go like crazy with modifying that. We will do that actually for the next session. But right now we want to focus on actually mapping those observations to good actions that can hopefully make this drone fly independently. So let's start modifying this file so it can look like this. I have it already pre-cooked, and I would leave it here as a memory aid. So we will just you can do the following thing. Go to Unity and in the script folder, you create a new one, and we will call it ML.
Diego, we don't see your screen.
Oh, sorry. Always forget about that very soon. Screen 2. Now?
Yeah, we see the Unity.
Yeah.
Excellent. So in Unity, create another script, C# script, call it like whatever you want. I'm calling it ML drone. What an original name. And I will reload everything. And I will just copy the content from the simple drone inside my ML drone, and I will change the name, of course, of the class. ML drone. Oh, why did I do it like this? Okay, doesn't matter. Ugly name. We're okay. And I don't know also why I got the gRPC input. It should look like this, right? If you just copy the script that I provided, and if you type it on your own now, it's okay. And because this is a new project, hopefully you're working in a new project. If not, that's okay. I didn't do a new project for this, for this demo. So you need to check first that when you go to packages, window package manager, in your project packages, the ones that are installed, you have Unity ML agents installed, right? So if this is a completely new project for you, you need to reinstall in Unity, not in the system with the terminal command with PIP. Here in Unity, the ML agents package. Because now, of course, we need to work with that. So once we do that, remember that we need to import ML agents, and we can say using Unity engine.ml, no, it's unity.ml agents. And also we need to get the sensors, unity.ml agents.sensors. And we need to modify our class, our drone, so it's not model behavior, but it's an agent. Now our class inherits all the agent methods. So from yesterday's class, who can remember what was the first thing that we actually did when we started programming our ML agent? What was the first thing we implemented, or the first method?
Awake.
Sorry?
Was it called awake?
We have the awake here. So
was it on input signal or something?
Sorry?
Was it an input signal or something like that?
The first thing that we need to implement is to say, what happens when our episode begins? Remember the on episode begin class? So we will put it here after awake. We will say like public override on episode begin. And if you remember correctly, this resets our environment to an initial state. Right? So it will set everything to the most basic. It was yesterday was only positioned for it was a random position for the target, and it was also a random, sorry, and the 0 position for the agent. Right now, we don't have a target, but we need a target. So the first thing that we're going to do here in ML drone is reference game object. And this will be a public game object target. Right? Because now we need to follow a target. And we will do something pretty similar to what we did yesterday. We want to set this target to be at different heights, but also at different, basically, distances from our drone. If you start training, for example, with a target in the same position, probably the drone will just get too comfortable. So if I go to Unity and I have my drone here, for example, and I will create a target. I will create this time with a sphere. And I will do this. Maybe I should change the color of the sphere as well. Let's set it to magenta. Okay, so imagine that this is the situation and you're never moving this. The drone might get too comfortable with just doing this every time and not even lifting, because it knows that it can increase the reward just by getting closer. So in this case, we will try different things, like setting a penalty if you don't lift off, for example. If you're in position 0, I will punish you. If you are too high, I will punish you. If you are between, for example, this altitude, I will reward you, right? So we need to do that so it doesn't get stuck in a comfort zone where basically just by doing this and never touching or getting too close to the target, it can basically maximize the reward, but never accomplishing what we want to do. That is one of the most difficult things for this specific agent that we're training right now. So let me return this to the position 0, 0, because that's where our drone wants to be. I lower a little bit in 0.5 the floor. Actually, I will name this the floor. And this is the target. Perfect. And let me reference this immediately. Build it. I need to go to drone. And it should show me. Oh, it's still using the simple drone. So I need to remove simple drone from my drone and add the new script that is called ML drone. So you see now, because it inherits from agent, immediately we have the behavior parameters. We have the script drone, the ML drone agent. And the difference with yesterday is that we are not having a specific or separate controller. Right now, what we have is the drone having the brain, or basically like the behavior controller, right? You can do it separately, it's okay. Some things will change, but you can add it here and just give all the intelligence just to the drone. Before it was just like a stupid cube controlled by another type of, for an external controller. So now let's see, we have the target. We will assign it immediately. And what we didn't do with this target was adding the tag target. Remember to add the tag. If it doesn't show here, you just go to add tag and you can add whatever you want. Okay, and could be target hey. And then you don't forget to select the object again and just give it the target. We're doing fine with time. That's good. Next thing that we need to do on episode begin is, again, reset what we're doing. So we will say that transform that local position is equal to vector 3.0. This will reset our drone. And in a similar way that we did for our target, pause for drone, sets random pause for target. And this will be something like target that transform that local position equals to new, you remember this, vector 3 random dot, oops, what happened there? That range, it was random that range. Oh, we want to use that random, so sorry, using random equals unity engine dot random. Yes, we need to add this so we don't get confused and we have a good random method. So we can do random range, and random range will be, in this case, let's say 0 to 15f, and just as we did yesterday, we can multiply this by random dot value less or equal 0.5, and this will give us a, sorry, with an exclamation, 1 or -1. Vector 3 does not contain a contrast constraint. Oh yeah, it's giving me that because I need to put the other arguments. So in this case, let's go back to Unity for a little bit. If this is our training environment, I mean, it's big enough so the drone doesn't go like away. You can see that right now the X position could be as big as 200, but we will set it not too far. Let's say that our limit could be something like 25 at the beginning. We can change that value later. So basically the random movement could be between 20 and -20. So to do that, we will replace this value here. We'll say 20. That's for the X coordinate. Now we need to do this for the height. We will use exactly the same. We will just change the values. This is for the Y coordinate, and we will say that the range will be between 5 and 20. So we don't want the target sticking to the ground. We want it as high as possible, but we also want to have, and actually we don't need this for the target. We just want values from 5 or 20 for this. And for the last value, we want, again, same as X, values that go from -20 or 20. So this will set at each episode these new things. Also, because we did a lot of physics modifications, we are adding, every time we fly, we want to also reset the rigid body. Why? Because if we are here and imagine that our drone starts flying, in the first episode, the drone starts doing this. getting force, adding the force, adding the force, adding the force. And if we don't reset the forces or the velocities, in the next step, if it keeps getting decisions, for example, to move the drone up, it will just keep going up and up and up and up and up. So we need to reset for each episode how the drone, basically the forces of this drone. Is that clear? Even also when we rotate and the velocity, we just need to calm it. We need to grab the drone and say like, okay, drone, relax. You don't have any force applied on you. This is a new episode. Now you will start like learning again and again, collecting new experiences. So to do that, it's really easy. We can just say RD that velocity is equal to a new vector 3, and that vector 3 will be 0f, 0f, 0f. No velocity. Also, we want, just in case, the angular velocity, we will pass the same. Also, we want to the rotation. Reset rotation, not only position. We will say that transform that rotation equals to quaternion, and that quaternion will get quaternion.Euler. By the way, if in case you don't know about quaternions, because those are a little bit like complicated, if you go to the most amazing explanation of quaternions from 3 brown, 1 blue, or 3 blue, 1 brown on YouTube, he has this interactive quaternion video that you can, man, that was it for me. It's so clear that you will never forget what a quaternion is. I'm lying because I already did, but I can watch the video again. So the rotation will be Euler, and we will pass the same thing, just the new vector 0, 0, 0. Not with that. And we are, one parenthesis missing. Yeah. I will compile to see that I don't have any errors. I don't have any errors. So until now, do you have any questions? I know I'm going a little bit fast. This is why I provided the code first and I tried to explain what this is doing. But right now we just need to modify this code in order to adapt it to our Unity agents. So the
Sorry.
first, yeah.
A quick question. So on line 79, you're using the RD.rotation. When you reset, you're using transform.rotation. Is it intended?
In line, yeah. This is because we are basically rotating. Can we do just transform? That's a good question. I don't remember why I did it like this originally. This is an old script, old code. Let me think about it and I will let you know. For now, let's leave it like this.
Okay, cool.
So we did the on episode begin. This should be good to go. Now we need to do the other method that is called, what was the second thing that we did yesterday? No one remembers. Collect the observations. Remember? First, now we need to learn. We're going to go through it. First thing that we need to do on episode begin, set the initial conditions for the episode. Second thing, collect the observations, basically establish what are we watching, what do we want to map onto actions, or what will determine, for example, how my rewards are assigned. So collect observations. For collect observations, we have the sensor. So sensor that add observation. There are other types of observations in case you're working with other like one hot, vector observation and things like that. We're just going to use this for this workshop. Add observation, and we said that we want in this case to use or observe the same things as yesterday. So this will be transform that position, local position, sorry. Local position. Excellent. Sensor that add observation, transform that, sorry, target that transform local position. Targets local position. Now, there is a difference now. Who can tell me, I mean, we added 2 observations, but what would be, in this case, the space size of these observations? No one?
So basically it's in
It's
3
6.
dimension for each.
Yeah, but two positions. So basically, like you have like 6.
Yeah.
Right?
Yeah, 2 by 3.
Exactly. So our size here, when we go back to Unity, because now we're watching 2 vectors, here the space size will be 6. We will change immediately in parameters this to my drone. Okay. Very good. If you add, for example, another observation, what can we observe right now? That can, what other parameter? Now, actually, we can use maybe like the minimum height as an observation. We can establish like a separate observation just for the height. But I don't know. Let's finish this first, and then we can add like more complexity to it. After establishing our observations, what else do we need to do?
Reward.
Not yet. Before the reward.
Actions.
Action.
On action received.
Exactly. Our famous actions. So a good way to do it, I'm gonna put this after the fix update. So I'm gonna say public override on action received. And here we're gonna do something. We're gonna work again with the discrete type of actions, because continuous, we're gonna use it tomorrow and probably it will make more sense, hopefully. We will work with the discrete actions. So first things first, we need to calculate, just like yesterday, v final distance to target, right? It's exactly what we did yesterday, not row 4. So we said that vector 3 distance is a float, a measurement. It's equal to the target transform local position and the transform local position, right? You're measuring the distance between those 2. After that, we create the variable that takes the actions create, and we will say that var action lowercase, sorry, action equals to vector action 0. And here, after the break, we will see that we have the option to play a little bit with this. In terms of how many branches of this we want. I want to have everything in just one branch to take my action, so I will leave it like this, and we will start creating now the behaviors, like the actions that this can take. But before that, we will actually put everything here, here. Should be 3. Oop, what am I doing? What? Okay, there you go. Between here and here. Okay. We will add the actions. We will add. But here we will set the same things that we did yesterday. So we will do it. Actually, we will do that after the break because we are just on time for the break. 20 minutes. If you have any questions, write it down, hold it there. You can ask it after the break. I hope this is going okay and you're excited about because you're like really quiet today. I hope
It's going great.
Raise your hand if you are okay. Okay, good. I mean, only a couple have the camera on, so it's too bad that I can't see your faces. So excellent, Pedro. All right, Ardavan. Okay, so we will have 20 minutes. So 4:07, we will return. We will finish this code and we will start training this puppy that hopefully you can train after this because it will take longer and it will be like probably a hard thing to do. I don't promise you the best results. I've done it, I did it, but it's up to you how to. We will also give you hints on how to tune this so you can have like another. You can play properly and configure your drone. And can't wait to see your results tomorrow, if successful or not, or your discoveries about this. Okay, 4:07, 20-minute break. Okay, we are good to continue. Here's my microphone. So, can you hear me well? Okay. So, where were we? I'm lost. Here. Oh, we were about to start writing the actions for our good drone. So, in this case, as I was saying, if we take a look of, let me remove this. Oop. I need to share my screen, of course. Screen 2. I need to move this here. So, as I was saying, we're going to map more actions. We're going to still use the discrete space. But for that, we need to establish first which are those actions. So we know that up and down are two actions, two possible. Left and right are two more. Forward and back are two more. And also rotation are two more. So in the end, we have 8 possible actions that we can take. But here in this code, I will try to do or modify one simple thing. But let's write the cases first, and then we will go through like the heavy modifications to what we need to do. Let me check my notes first. There you go. So we will come here when we have actions, and we will switch cases. To do that, we need to do just like yesterday, switch action, and we will create our cases. Case 0, we will name it here, move up. Case 0, we'll add here a break, and let's add the remaining 7. So this will be case 1, down. This will be case 2. This could be rotate right. This one here can be rotate left. This will be case 3. This will be moving forward 4, backwards 5. We need 2 more. One will be swerve right and swerve left. We're going to call it just move left here. will be 6. Finally, move right will be 7. So now we have our 8 cases. What I also need to fix here in the fix update is to say that if is manual equal true, I will have the possibility of driving my drone, right? I don't want these actions to be executed here or watched here. So only if we have the manual mode activated, we can control our drone like if nothing was happening. Else, what can we do here? Else, we're not going to do anything. So we can erase this actually. Maybe we will add things later. But we need to make some changes to our methods because right now, basically what we will call these functions from the cases. So we need to separate a couple of them. So we already separated movement up from movement down. So now we need to do movement backwards. And to do this will be like super easy. So I will put move forward first. I will separate this here. If we go, let me put some order to the code. We have movement up, movement down, movement forward. We will copy this method. And we need to see what is the difference. So this will be backwards. And the difference here is oh yeah, we need to make modifications to all of our methods. So for now, we will just leave this like this. Movement up, down, movement forward, movement backward. Rotation, we will split it in 2. This will be rotation left. This will be rotation right. The swerve also will be in 2. This will be left. This guy will be right. For now, we will leave this untouched unless we will modify this at the end because we need to do one small thing. So, yes?
A quick question. If I understand, you're trying to assign all these methods to the different cases, right?
Exactly.
Like so they're you can use either manually or use depending on the automatic action.
Exactly. Because if we have time, if not, I can provide an extra video later how to do the demonstrations manually.
Mm-hmm.
So basically you control with the joystick, for example, the drone, and you show the agent how to perform the task. And then with those demonstrations, you train your model.
So you're supervised learning with
you're doing
imitation
learning. Yeah, you're doing imitation learning. So that's the idea of making all this like chunk of code. So let's modify this. So we're saying that if in the movement up first, if is manual, do the typical thing, else Here we just need to modify minor things. Oh, let me check my notes. Yeah, we just need to say that the force is for 50 because we don't need intervention from a human. So basically, if we select the movement up force will be that. And let me check just one thing to do. And we need to add this force actually, but we will do that later. But we need to actually add it to the rigid body. Movement down is else, and here we will say that the up force, just like here, is minus 200. For movement forward, we can say movement forward. We can do the following. And this is a little bit weird in terms of what we are going to do. We are going to introduce a new variable that is called move. Let me add it here first. I don't know how to call it actually. Don't mind about this, these errors. How can we call it? Movement variable, whatever. This will be a float. We'll call it move, and we will leave it to 0.5 f. If we go down here in movement forward, you can see that here the way you're adding the force is according to how are you getting the values from the vertical axis. So in this case, these are values that can go from -1 to 1. So you can basically say that move is 0.5. We just leave it like that. We can also like add another type of modification, but right now we just give it a constant 0.5 that will add. So this will move our drone in that direction. To calculate the tilt amount forward, we apply the same thing. And then we say that the up force, and I will explain this immediately, is 98.1. Why are we doing this? Because right now, we are not calling the difference with the simple drone that we have here. Actually, this should have been like a one method. Probably the script that I shared with you is different. I used to have this method integrated. So basically you can say also, if you're not pressing up or down, basically you will let the drone hover. So you need to give some, at least constant force. So in this case, because we still want to, if the drone shoots, basically is in the air, and we move left, for example, we don't want the value to decrease to 0 or -200 too fast. So we still need to give it a little bit of propulsion up. You will see that this will work. We can modify it later. So this is why we are going to say this. So for movement backward, we will do exactly the same. But here, actually, we can give a negative value. So we can do exactly in forward. Here we can say else, and we can say that RD. Check that I'm copying exactly the same here and just replacing input get axis vertical, and we can say that this is minus move. This is replicating if we were like moving the joystick, for example, like in the opposite direction, like moving backward. That's great. Those methods are complete. For rotation, we will do a similar thing. Else, and here we're gonna stay first with the rotation left, that is the minus. So I will erase this, and I will say that this is what's gonna happen. The wanted rotation left. And then basically we want to do the same calculation here. Yeah. This is what's going on. So if we don't have the manual input, we just add this automatically, these values and calculations. And here it will be also good practice to keep the propulsion up. So if this gives us like weird results, we can comment it, but I think this is going to work. This is just a recent modification I was trying before the class, so I hope it works. If not, I was wrong, of course. And for rotation right, now we need to delete this one. Sorry. Yeah, for rotation right, we delete that one. And we just say here, else. And we wanted Y rotation. We'll be adding the rotate amount by keys. And then we will calculate that rotation again. We will add the damping, and we will add the up force. So we are good to go with that one. Now, to incline to the left or to the right, here's a little bit trickier, I think. So let's see how can we do this. Else, we are, I think, okay in time. Yeah, we're good with time because after this, we're just good to go and train this. Just give me 1 second. Should I use this or not? Yeah, probably I should do it anyway. Okay. So we can copy this again. Exactly what is there. And replace this for move again. And replace this by move again. Just like a constant 0.5 value that we can modify later. And also here, we will see that we can modify it and do other stuff. So if we do this, we are fine. And we can also add here the up force. And this is with upper U. For the swerve, left and right, this absolute. This is left, so it's minus 20. And this is, sorry, if this is left, this is minus 20, and this is right, is 20. Okay, I had a typo here. So we do the same thing. Sorry that this part is like a little bit boring. We're using code, but you will see that hopefully it will work. And we replace this with move. replace this with move. And we replace this with move. Okay, and let's add the up force here. And now we need to finally modify this one here. Oop. Okay, it's giving me some errors that I need to fix later. But here, what we want to do is the following. We will copy exactly what's inside this if statement. Again, we will say else, and we will proceed as usual with the value replacement. Everything here will be replaced with move. Because for now, again, the drone wants to have just like impulse that are fixed, just to see if this kind of works or not. So move, move. Again here.
I have a question.
Well, okay.
I was just wondering if there's a reason why instead of having this if statement for the controls in all your statement, you aren't using the heuristic class that the agents have, where it's sort of the same thing you're doing, but it's just you just have to put it in one function, basically, the heuristic function.
Yeah. No, it's just because it's just another way of doing it.
Okay.
I mean,
Yeah, I was just wondering, like, if there was a benefit or a
No.
different. Okay.
It's just a different way. I mean, you will find many ways. Even I remember in the examples from one of the versions, it was done like that. So I don't know. For now, we'll just leave it like this. It's a lot of code repeating, but not efficient. I am an ugly programmer.
No, I didn't mean it like that. I was just curious if there was.
No, actually, I am. My code sucks always, like in terms of organization or whatever. So I think with that, we should be okay. We just need to fix one thing here, a couple of things. This is backward rotation. What was the name of this? Function was here. We just need to put the right functions here. This is rotation left, right, swerve left and right. Okay. We said that the else doesn't matter to us because here, now we can finish the part for our actions, where we are going to assign for the case 0, move up. We'll say movement up, movement up. Yeah, that's okay. Movement up. And when we basically go up, when we call that function, we want to add relative force that was calculated for that function, vector up, vector 3 dot up, times the up force. So you understand this? Basically, when we call that function, that will give us the value, the movement up, and then we add that force to our rigid body. And after that's done, we just break and we are okay with our first action. Now, for movement down, we call movement down, and we do pretty much the same. We call the add force vector up, the add relative force vector up and up force. In this case, we know that movement down will give us by default a negative value, so that's okay. Oh, sorry, I'm moving my window so I can also have you on my screen. So we do that, we're okay. Now for movement right, let's see. Movement or swerve right, actually. We can do swerve right. And here we want to modify the rotation, add it to the rotation, RD that rotation equals quaternion, not identities, we need Euler, and we need here new vector 3, and the things that we calculated before, the tilt amount forward, that will remain exactly the same, the current Y rotation, and here it was the tilt amount sideways. We will get a positive value for this one. So this will allow us to go to one direction. In the case of move left, we will copy exactly the same. But instead, this will be left. Good. For moving forward, move forward. And here we need to also do exactly the same. Copy this line, because these already have like this. You just keep adding forces. Basically the rotation, sorry, according to what's happening if you choose one action or the other. Here, forward, sorry, this is move forward. Okay, and this is move backward. Is this the name? Capital B. Okay. Now this is rotate left and rotate right. Rotate, same thing. Rotate left. Do I have the method here? Rotation left, sorry. Rotation left. Same. And here, copy that line and we say rotation right. And that should be it for our actions. So now we need to set the rewards. For the rewards, we do exactly the same thing we did yesterday. We say that if this float distance to target it's equal to vector 3, and it will be target that transform that local position, comma, transform that local position. Good. New vector 3, sorry, oh, sorry, vector 3 that distance. That distance. All right. And again, we need to check if the distance that we measure before taking an action decrease or increase, that will set a reward. So to do that, we will say if distance to target is less than final distance to target, what if not float? If we can set the rewards. These rewards will change eventually according to what we're doing. So we will start with conservative values, add reward. You can also have, for example, equations that set the reward according to the height. So we can say, for example, here, add reward 0.1 times transform that local position that y. So this will be a variable reward. That actually, this is a good practice because the higher we are, basically this will be an incentive to our drone to take off. So we can try something like that. So 0.1 f times that. But it needs to be a small reward, because if it's too high, the drone will only care about just going up, right? So, but we can contrast this with another thing, like if, for example, the height is the y value is super high, you will get punished. So this will force you also to. So it's a matter of equalizing the different variables and rewards that you have. So we will see that this is not like exact science. And I remember when this finally worked, when I did it for the first time, it was like a little bit problematic to make it work. So we have that. Now we will say else, and we will punish this guy. And we will say that add reward is, let's say, -3 f. We will give it a huge punishment for this. What else we can do? We're not going to use the collider this time. We will not complicate stuff. So one thing that we can do in this case is just saying that if distance to target, the final distance, is less than 0.1 f, which is a very little, right? If that distance is 0.1 f, basically you're touching the target, right? You don't need to collide right now. You're so close to the target that the target is, you want the reward for hitting the target. So here we will say add reward, and we will give it, like in this case, because it's more difficult, 50 points. This will boost our training. I don't know if you had the time to train the exercise yesterday. If you, or you can do this with the files that I provided. Try to train the agent that we did yesterday without this reward of touching the target. Just when touch the target, when it touches the target, just like end episode, and you will see that it will train eventually, but it will be way slower. And this will give a boost on like trying to find the target. We can add a couple of more things. So we can say, as I was saying, if transform that local position is bigger than we were giving to the drone, the maximum height was 20. Let's say if it's higher than 25, we will give a negative reward. So in this case, less than 25 f, sorry, position that y is bigger than 25 f, add reward, and this will be, let's not be so hard, 0.2 f minus 0.2. And at the same time, if this will be probably like redundant, but I'm gonna try anyway. Who knows? If transform that local position, that y is less than, let's say, 2, less than 2, this will also have a negative reward. We don't want this drone to be lazy and stay on the ground. So we will force it to at least try to, it's like a small push. So it knows that if it lifts a little bit, it will realize that also that just by going up a little bit, it not only have a good thing in terms of rewards, because you're not getting punished, but also you're getting rewarded because the distance, of course, to the target will be less. So that, you see, you start like micromanaging this reward system. So hopefully,
Good question about this reward. Are you assuming that the target's always flying?
Yeah.
Okay.
So it's a good thing because that's a very good question, because here now we will have the target in different locations like all the time, flying. And at some point, we might use this training file. For example, if we are combining our agents, the robotic arm with the drone, with a small like guy that just goes on a plane. So you can say, oh, the small guy with the small cube that only moves in X and C basically drops something. The drone needs to basically go down to that position and leave it in front of the robotic arm, for example. For that, in order so the drone can understand to go really low, you need to train it with that. For now, you need to train some low positions and not punish those low positions. So, but for this case, we just want to teach it to fly and to go to a target. So this is why, I mean, I'm adding all of these restrictions that maybe they will work, maybe they won't. So we will say also this is 0.1. No, that's not 1. But we can play with this. So if everything is finally okay, it's time to train this puppy. So here's our drone. Here's this. I want to make a couple of modifications. I want to set a couple of walls so the drone don't fly away. So that is good. So I'm just copying these planes. Just minus 90. Okay, copying the planes. I'm copying another plane here, and this should be 90. So for example, if I'm doing this, one other like good suggestion for our training, so you want to keep the drone confined to this cubicle like a scenario, you can say if the drone touches the wall, get punished. So you can add, for example, colliders to these walls, and that will also punish the drone. You can add obstacles and do the same thing. So now we do this. We will rotate this in -90, and we should be good to go. Let me just, for the sake of whatever, I'm gonna paint this green just to differentiate. Can I change the light? Probably yes. Oh, too hard of a shadow. It doesn't matter. We have two black sides. We're gonna watch everything from this perspective. So we're ready to go. We just need to configure one final thing. If we go to our drone, this is called my drone. We know that we have 6 observations, only 2 things that we're observing. We could add more, whatever you want. Basically, the more observations you have, the more precise. So also the height could be an observation. And what does that mean? That are things that you're just looking so that the neural net can basically have more information to take the right decision. Right now, it's only the distance. We will use the discrete space. We will use only one branch again. We will go simple because this is already like complicated enough with 8 basically numbers. So it will go from 0 to 7. And with that, we should be okay. We have the max steps. We're gonna set it to, I'm tempted to test with a high number, like 600, but probably we want to do less. So we want to push the drone to complete the task as fast as it can do it. We are going to disable the is manual, so we don't move the drone with our keyboard. And we need to add the decision requester. So if we add the component decision requester, that will help us to also to tune how our agent performs during the training. In this case, I will leave it first to a low decision period. So basically, it doesn't take many decisions at the same time, because when you're working, now we're going to work with inertia, basically. So imagine if you're making a decision, you're running. Imagine like the typical, like you're running so fast, and you're decided. The decision is, oh, I need to run. You apply the force, and because things are happening so fast, you decided to keep running, but you suddenly realize, oh, damn it, I should have turned left. So basically, if the decision period, if it's basically shorter, it would allow you to take fewer actions. So I don't know if you saw the training yesterday. We had to crank it up to 20. So this thing was like taking a lot of decisions per hour, like per frame, and it was performing really well. Probably here we don't want that. We don't know. I mean, we don't know. So again, just to train this guy, do you see the terminal?
Yeah, we see it.
Yes.
Good. Excellent. So let me see what we have here. CD day 3. 3 UAB assets config and here I just have the basic YAML file, like the word YAML file. So we can start training our our body. But first, let me check the file, the YAML. I will use SAC, Soft After Critic, is the one that we will use from now on. I will explain it better tomorrow with the other example, the robotic arm. Actually, already the behavior is called drone, so we might want to change that here instead. We don't want to mess around again with that, so it's just drone. We go back here and we do ML agents learn basic dot YAML run ID.
Learn is spelled wrong.
Yeah. Learn. Thank you. Run ID, we will call this DR01. Oop, ML agents.
There should be a dash between ML agents and layer.
Oh yeah, you're right. Thank you. So you see, this is working. It's waiting for this. Hopefully it will start doing something. Oop, it is flying. It's doing stuff. It's kind of crazy. Let's see how the reward is going. But the good thing, so you see, let me move the camera away. Actually, we can watch this here. So you see that the target is just like, wow, this is, hopefully it will train. It's kind of like flying away. I don't know why, it's a strange behavior. But hopefully at some point it will start doing better. Oh, I messed it up with the camera. Cannot see anything. So can you see that the drone somehow it's learning how to fly, but it's not flying probably like correctly? Let's see what we can change. Maybe the force that we are applying, it's too much. So it's just like taking off and going to the infinite. So the good thing is that we can change this on the fly and see what the results are. Probably we will mess our training, but it will help us to realize a couple of things. Also, let me stop this and I will show you one other thing. Okay, object, okay, that's okay. One more modification to our code. We want to debug what action is. Debug.log action. Because we want to see what type of decisions this drone is taking, right? If it's taking like only lifting off or moving to the right or whatever. So we want to see that. I will do it again. Go to Unity, and actually for the parameters, so it doesn't go that crazy, I will also like to increase, for example, the mass of the rigid body to 15, maybe a little bit more heavier. Also, I would like to for now, let's leave it like this. I will try to leave it with one decision period, like a low decision period. So I will do this. I will change the name to drone02 or DR02. And let's see how this thing starts training. So again, this will take more time. And it's good. You can see here, if you press the collapse, you see that here is giving me a 3, a 7, a 1, and whatever. These are all the decisions that right now this thing is taking. So right now, the thing that is doing the most is just like circling around. Sometimes it wants to take off. Also, it's doing action 6 that, according to the code, action 6 is this one, rotating to the left. Is doing it a lot. Probably because it's heavier, it's doing this thing, and the decision period is slower. So check, for example, when I increase the decision period so I can do more stuff.
Diego,
Yeah.
don't you think like it would be nice to add maybe velocity, acceleration forces to the state space, to observation space? Because otherwise the drone will think that whenever it's really fast or it's not, as long as like the position, rotation are the same, it's the same state, right?
Sorry, can you repeat?
In the observation does not consider like velocity or acceleration or any force, right? Right
Yeah,
now.
exactly. No, it's
So,
not considering anything.
okay, I'm just curious, like maybe just adding those things will make it easier to learn.
Also, yeah. Exactly. This is why I'm saying this is just like the most simple training with just those 2 observations. And it proves that somehow it's learning how to fly. So you see it's going up, but probably it's going with too much force. So we need to tune that parameter as well. So I will leave it up to you to train those things. So for example, what other parameter would you like to observe? Like it was like very interesting. Yeah, like of course, like velocity, and also you can try to, I don't know, check, for example, for the angle. So the drone can be as horizontal as you want. And that, for example, could give a reward or another metric. So right now, I'm just going to leave it training. At some point, hopefully we'll get better in terms of the mean reward is doing catastrophic. It's like really, really bad. But probably it will increase at some point. We don't know yet, right? So,
but if you look at the action, it seems to be it's always taking 0 and not doing anything else.
yeah, exactly.
It is okay. Like it's not something going wrong.
Probably it's something at some point it was taking 3 more than others. So probably it's because so if you play with the decision period, probably you will see that it will start taking other. So this is what I was saying. So now you see it's like just rotating and it's doing other stuff. It depends on how you tune the parameters. And if you give this less time to decide, and also, for example, the max steps, you reduce them, you can force the drone to take like probably like better decisions. I don't know. There's a lot of things to play. I will try to leave it with a couple. I will actually train after this class. I had to go to a work meeting, but I will leave it training, and then I will train it again during the night with other options to see probably what were the outcomes. So this is why for now I'm just leaving it to you. So you see now that I changed the decisions, the option 0 stopped being the fastest, but now we have decision 4. So now it's like going, it's trying to take off, it's rotating. So maybe one thing will be just reducing the amount of actions and just starting with, okay, what if I just constrain my drone to go up first? Just go up, go up, go up. That's an easy one. And the only action that you will get is just like taking off. And then what if you have like going down, then moving to the side? I mean, it's up to you. I don't know. I mean, I hope it works. I think this is a fun example to show you. So I hope you can try with it and combine with tomorrow's exercise. If it works, tomorrow will be like, I mean, one that I really enjoy. So don't forget to actually model your 3D arm. I will leave available in the same folder, the Dropbox, the Rhino model, so we can work tomorrow on that. Yeah, it's doing really bad, but let's see what happens when I train with better parameters. This is a really, really complex thing to do, by the way. So I don't expect that this is super successful. Yep.
Could you post the finished ML drone script on the Dropbox as well?
Yeah, I will put the full project.
Great, thank you.
Okay, we are on time. Again, I need to run because my boss will kill me. Sorry that I cannot stay longer. I will try to answer all your emails tonight. Sorry, but they are just giving me too much work and I'm going a little bit crazy. So, and I need to sleep as well. Okay. The good thing is that I just stream all the video on YouTube, so it will be immediately there. So you will find video 2 and 3 on YouTube immediately. So thank you again. It was really fun. I hope you had fun as well. So I'll
Thank
see you
you.
tomorrow.
Yeah. Thank you.
Yeah,
Bye.
cheers.
Thank you very much.
See
Take
you.
care.
Bye.
See you.
Have some sleep.